6.1 Systems of Linear Equations. In this section, we are going to learn solve the system using the substitution, using the elimination, solve the systems with infinitely many solutions, solve the inconsistent system, solve the system involving 3 equations in 3 variables, and then solve for the applications involving the systems of equations. So we start the first one using the substitution method. We look at the example here. We have 2 linear equations with 2 unknown variables. When you have 2 unknown, you need 2 equations in order to solve it. When you have 3 unknowns, you need at least 3 equations to solve it. So this example gives us 3x plus y equal 1. Another equation has negative x plus 2y equal 9. Using the substitution, we can target in the one single variable first. So we did a y equal 1 minus 3x. When this 3x move to the right hand side, turn to the 1 minus 3x. And then you substitute the y part into the second equation of the y. And once you have the y substitute into the second equation of the y part, you rewrite the second equation into the negative x plus 2 multiply 1 minus 3x. This is a y. Close it and set that equal 9. Doing this way, you will rearrange your equation from 2 unknown variables narrow down into the single unknown variable. As here you can see, from the second equation here, you only have the single variable x remaining. And then from here, we combine like term. You get a negative 7x. This number 2 bring to the right hand side is equal 7. Then you divide by negative 7 on both sides. You will solve the single x equal negative 1. Once you have the x solution ready, you can plug in this number back to this part. So from here you can solve for y. So y is equal 1 minus 3x. You substitute negative 1 into it, you will solve for the y equal 4. So the solution has 2 unknown variables. So this is an ordered pair with a coordinate ordered pair, x equal negative 1 and y equal 4. Another approach to solve for systems of linear equation, we go with the elimination. So we take a look at the example. If you are interested, you can read the instruction of the strategy how to solve a different approach of the system equation. But now I'm going to work on the example. So this example has 3x plus 2y equal 8. 2x minus 5y equal 18. From the equation, I know it is not a good approach if I go with the substitution, because I don't have the single x or single y from either equation. So the best way to approach this question, we go with the elimination. We eliminate one variable first. So you have to decide which variable you want to eliminate first. So we can do the example here. Because both of the equation, they don't have, so we have to determine which variable you want to eliminate. If I want to eliminate the y term, that means I have to make the coefficient number of the y term on both equations into the same number, then I can eliminate. So we use the LCM, least common multiple, to find the same number of the y term. 2 and 5, the least common multiple would be 10. So we multiply 5 into the first equation, multiply by 2 into the second equation. So the entire equation you multiply with 5. So we rewrite it. It will turn to 15x plus 10y equal 40. We multiply by 5. Multiply by 2 into the second equation, you will get a 4x minus 10y equal 36. Now we have the same y term, the same numerical y term. Then we can start to eliminate. Keep in mind, the y term here, these two y terms, one is a positive, the other one is a negative. In order to eliminate, we need to add both of the equation. So that your positive 10y minus 10y, they will cancel out, turn to the 0. That's what we want. So we have to add. So if I label this equation is number 1, I label the second equation is number 2. So we combine 1 plus 2. We combine both of the equation. So 15 plus 4, you will get a 19x. 10y minus 10y is 0 out. 40 plus 36, you get a 76. Now divide by 19 on both sides, you will solve for x equal 4. Once you solve the x, we can simply plug in this 4 back to any equation you wanted. But normally, I recommend you substitute this number back to the original equation because the number is smaller. So when I substitute the x back to the first equation, we have 3x plus 2y equal 8. That was the equation. Now we substitute the x with 4 into it. So you have the 12 plus 2y equal 8. And then from here, you can solve for y is equal negative 2. So same way, the ordered pair solution is x equal 4, y equal negative 2. Sometimes, when you have two systems of linear equations, for some reason, by the end, when you solve it, it turns to a 0 equals 0, or 2 equal 2, or negative 4 equal negative 4. So that means this is a true, right? This is a right statement. This is true. So in that case, you will have many solutions. Many solutions. We call identity. That is on your chapter 1. Identity equations. So in that case, we know one variable is rely on the other variable because they are rely on each other. So when you have the solution, by the end, it gives you the number are equivalent on both sides. We know those type of the system of linear equation, they are dependent equation. They rely on each other. Okay. Form the solution. So the way we give the solution, we always keep the x term. Alright, this is the input. So we need to keep the x term. Now the y, we don't write down the y here because your y is rely on the x term. So from here, if I rewrite the y, we're talking the single y, so keep the 2y equal 3 minus x. Divide by 2, you will get a y equal 3 minus x over 2. X plus y equal 4. X 2x plus 2y equal 8. Now, this system of linear equation, when you solve it, you'll get a number 0 equals 0 by the end. Okay? We will do another example to show the processing, how to get a 0 equals 0 or get a number equal on both sides. And then from here, provide the solution to satisfy this system of linear equation. We keep the solution of the x term, just keep the x. Now the y term, we don't write down the y because you have the identity. You have the dependent equations. So the way you can solve for the y, you can use any equation here. I'm going to use the first equation. X plus y equals 4. We are solving for y, so I keep the y by itself. Bring the x to the right hand side. I let the y equal 4 minus x. So that means as long as you give me the x value, I will solve for y. I just substitute the x into here, then I will give you the y. So y is the dependent of the x term. So this is the way you perform the solution. When you have two equations, they are dependent equations. Another case would be you solve for two systems of linear equation, and by the end, you get a 0 equal 1 or negative 4 equal 2. This is not right. This is not the true statement, right? So this is a false statement. In that case, you just write down no solution. Because it's no solution, there's no need to find the x or rewrite the y into the x term. No, because you don't have solution. So we call this type of the equation, they are inconsistent. There's no way you will find it. Alright. Look at here. If we graph each equation in this system, that means inconsistent, the graph will be parallel. So you'll see the two lines. They are parallel. They have the same slope. They never touch. And that's the reason why you don't find the solution.